An electrical dipole and flux lines, or we call that electric dipole. An electric dipole is formed when two point charges of equal magnitude but opposite signs are separated by a small distance. They are moving freely, but they are separated by a small distance and they have opposite charges. Okay, so the idea of electrical flux lines, or we can say electrical lines of force as they are sometimes called, was introduced by Michael Faraday in his experimental investigation as a way of visualizing the electrical field. An electrical flux line is an imaginary path or a line drawn in such a way that its direction at any point is the direction of the electrical field at that point. In other words, they are the lines to which the electrical field density D is tangential at every point. Any surface on which the potential is the same throughout is known as the equipotential surface. The equipotential lines, the intersection of an equipotential surface and a plane, result in a path or line known as an equipotential line. No work is done in moving a charge from one point to another along an equipotential line or surface, because VA minus VB is equal to 0, and hence E dot dl is equals to 0. Polarization in dielectrics. The main difference between a conductor and the dielectric lines in the availability of free electrons in the atomic outermost shell to conduct current. But on the other hand, although the charges in a dielectric are not able to move about freely, they are bound by finite forces, and we may certainly expect a displacement when an external force is applied. So that means some of the particles, they can't move freely because we say they have the small distance, they have the different signs of electrons and they have the small distance. That means they are bounded by finite forces which may expect some displacement. Okay, to understand the microscopic effect of an electrical field on a dielectric, consider an atom of the dielectric as consisting of a negative charge and a positive charge as shown in the next figure. If you can see, E is equals to 0, and here E is equals to have positive and negative charges, but they are attracted or something by someone. So polarization of a non-polar atom or a molecule. A similar picture can be adopted for an electrical molecule. We can't treat the nuclei in molecules as point charges and the electronic structure as a single cloud of the negative charges. So you can see negative charges are attracted towards the positive charges. You can see, since we have equal amount of positive and negative charges, the whole atom or molecule is electrically neutral. When an electrical field E is applied, the positive charge is displaced from its equilibrium position in the direction of E by the force. So this force is some external force, while the negative charge is displaced in the opposition direction by the force. A dipole results from the displacement of the charge and the charges, and the dielectric is said to be polarized. In the polarized state, the electron's cloud is distorted by the applied electrical field E. This distorted charge distribution is equivalent, by the principle of superposition, to the original distribution plus a dipole whose moment is P is equals to QD, where D is the distance vector from minus Q towards positive Q. The Q is referred to as charge of the dipole, as you can see in the figure. If there are n poles in a volume AV of the dielectric, the total dipole moment due to the electrical field is given using the superposition principle. As a measure of intensity of the polarization, we define polarization P in coulombs per square meter, this is the unit, as the dipole moment per unit volume of the dielectric is. is equals to limit delta V is approaches to 0, sum of k is equals to 1 to n q k dk over delta V. Thus we conclude that the major effect of the electrical field E on a dielectric is the creation of dipole moment that align themselves in the direction of E. This type of dielectric is said to be non-polar. So, examples of some non-polar dielectrics are hydrogen, oxygen, nitrogen, and the other rare gases. Non-polar dielectric molecules do not possesses dipoles until the application of the electrical field, as we have noted before. So examples of polar dielectrics are water, sulfur dioxide, and hydrochloric acid have built-in and permanent dipole that are randomly oriented as shown in the figure, and these are said to be polar. Okay, so permanent dipoles which have E is equal to 0, or alignment of permanent dipole when we have E is not E is equals to 0.